Hey everyone, welcome back to another explainer. Today, we're taking a pretty dense review worksheet for Cambridge IGCSE Additional Mathematics and transforming it into a totally clear, logical progression of problem solving. By the way, if you find this helpful, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Now, if you've ever stared at a page of equations and just felt, well, completely overwhelmed, you are definitely in the right place. We aren't just going to solve math problems today. We're going to decode them. We're going to see how these abstract numbers on a page actually translate into the real world. Okay, so here's our roadmap for today. We're grouping these exercises thematically, starting with the power of derivatives, optimizing the real world, reversing with integration, trigonometry and curve areas, and finally, kinematics, which is quite literally math in motion. Let's dive in.
Section 1. The power of derivatives, focusing on mechanics and tangents.
So, our first real conceptual leap is understanding how derivatives actually find the rate of change. Think of differentiation as this incredibly powerful magnifying glass. It lets you see exactly how steep a curve is at one single microscopic point. Looking at the slide, it brilliantly illustrates how applying the quotient rule transforms our initial equation into a powerful new formula for the slope. On the left, we've got a function with an exponential divided by a variable. By carefully applying the quotient rule, differentiating the top, multiplying by the bottom, subtracting the derivative of the bottom times the top, all over the bottom squared, we get that intimidating expression on the right. But don't let it scare you. It's really just a machine. You plug in an x value and boom, it instantly spits out the exact gradient of that original curve. Now, what's genuinely cool about this is how we take that theoretical derivative and actually use it to find the exact tangent line at a specific point on the curve. This right here is a classic Cambridge exam scenario. We're given a curve equation and an x-coordinate, which is 1/3, and we have to find the equation of a straight line that perfectly grazes the curve at that exact spot. By substituting x equals 1/3 into our newly derived gradient, we smoothly arrive at the final tangent equation, 5x minus y plus 9 equals 0. Notice how clean that final format is? There are no messy fractions anywhere, just pure mathematical elegance. Moving right along to Section 2, optimizing the real world with the cylinder problem. Let's see how all this pure algebra actually helps us optimize physical objects. This is the exact moment where calculus stops being just numbers on a page and becomes a legitimate tool for engineers and designers. We've got a classic optimization hurdle here, a container with a fixed volume of 1,000 cubic centimeters, and we need to use calculus to minimize the surface area. Imagine you're actually manufacturing these things. Every extra square centimeter of material is costing you money. Your job is to hold exactly 1 liter of liquid, that's the 1,000 cubic centimeters, while using the absolute bare minimum amount of metal or plastic. So, the crucial point here is breaking the problem down into these 3 logical steps, so we aren't juggling a million variables at once. Step 1, we use our volume formula to write the height in terms of the radius. Step 2, we substitute that right into our surface area formula. Suddenly, our area is an equation with only one variable to worry about, the radius. And step 3, that's the absolute magic of calculus. We find the derivative of the area and set it strictly to 0. Why? Because setting a derivative to 0 finds that bottommost dip of a curve, the exact minimum point. Once we set that derivative to 0 and solve for our ideal radius, we just plug it back into the area equation. And look at that! We discover the optimal surface area is exactly 439 square centimeters. It is so satisfying to take a messy word problem, structure it mathematically, and get a definitive, optimal real-world answer like that. Okay, on to Section 3, reversing with integration, moving from derivatives back to curves. Now that we're pros at breaking things down, it's time to reverse the process and build them back up. If differentiation breaks a function down to find its rate of change, integration is essentially the art of reassembling it. This problem tasks us with integrating not just once, but twice. And we have to use our starting conditions to find those specific constants of integration along the way. We start with the second derivative, the rate of change of the rate of change. We integrate once to find the first derivative. But remember, every single time you integrate, a wild constant c appears out of nowhere. That's exactly why we're given those initial conditions, x equals 0 and dy over dx equals -2. So we can solve for that first constant. Then we just do it again. We integrate a second time to get back to y, which creates a brand new constant. We use our final condition to solve for it. By carefully reversing the calculus step by step, we successfully reconstruct the original curve's equation in all its glory. Look at how beautifully all those pieces just click together.
Moving up a gear, Section 4, Trigonometry and Curve Areas. We're talking identities and exact values.
Stepping up the complexity, we are now merging our integration skills with the sometimes tricky world of trigonometric identities. Before we can even think about finding the area under this curve, we absolutely must leverage this foundational mathematical identity to simplify the expression. Seriously, trying to integrate tangent squared directly is a complete nightmare. But by substituting it with secant squared minus 1, we transform what looks like an impossible integral into a standard rule that we can easily apply.
Now, pay close attention to the wording here. Because the question explicitly asks for the exact area, we know for a fact we must keep our answer in terms of pi and certs. No reaching for the calculator to get decimals. When you see a curve bounded by x values like this, you know you need to set up a definite integral, using pi over 12 and pi over 3 as our boundaries. Applying our converted secant squared integral and evaluating those boundaries gives us this beautifully precise, exact mathematical area. Leaving the answer as pi over 3 plus 8 minus 2 root 3 might look a bit unfinished if you're not used to it, but to a mathematician, it is absolute perfection. It's a completely lossless representation of the exact area. And finally, Section 5, Kinematics, Math in Motion. For our final act today, we're applying everything we've just reviewed to the physical motion of particles. This is kinematics, where math truly breathes life into physics. This table cleanly extracts the data for both particles in the problem, showing us exactly what we're looking for so we don't get lost in all that dense text. Particle P is rolling with a velocity time graph, while particle Q gives us a trigonometric equation.
To solve this, just remember the golden rule. On a velocity time graph, a completely flat line means zero acceleration. If your speed isn't changing, you aren't accelerating. And the area underneath that velocity time graph gives us the 110 meters of distance traveled. You literally just calculate the areas of the shapes formed by the graph and add them up. It's geometry meeting motion.
But for particle Q, we have to shift back to calculus. We've got a velocity equation, but we need information about acceleration. We have to differentiate our velocity equation to find the acceleration, and then figure out the smallest positive time where that new equation hits 0.
Differentiating gives us an acceleration of 6 cosine 2t. We set that equal to 0, and using our knowledge of the cosine wave, we know it hits exactly when t reaches pi over 4 seconds. In less than a single second, that particle experiences a literal moment of 0 acceleration. Crazy, right?
So, bringing it all together. Group your problems by concept. Break those multi-part word problems into discrete equations. Use your core identities to simplify things before you integrate. And always remember, the derivative of velocity is acceleration. By systematically applying these structured strategies, you can take a super intimidating page of equations and turn it into highly solvable, logical steps. The math you're learning here isn't just about passing an exam. It is quite literally the underlying source code of the physical universe. If abstract calculus can perfectly predict the acceleration of a moving particle, what other invisible forces in the world around you are just waiting to be mapped by an equation? Think about that for a second. And hey, before you go, don't forget to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Drop a comment below if this helped, and I'll see you in the next one.